Good day. Good day for everyone. I'm Nemeka. I'm Samuel. Can you make me equal so I can share my screen?
You can share now. You're now equal.
Thank you. Okay, so good day, everyone. It's nice to have you guys here again. I'm Nemeka. I'm, I'm hosting this webinar from Enugu, Nigeria. Nice to have you guys here. Okay, so today we'll be talking about um, neural networks, right? What neural networks are, and how they work, right? So let me share my screen. Okay. I hope my screen is visible. Okay. So good day. To be a quick one. Um, okay. So I just want to ask. You can type in the chat that probably some of us say, or most of us say, know what neural networks are, right? About now, we know what neural networks are. We have a picture of what it is. I'm going to build on the fact that you know how neural networks work, like general, right? Before, like, so I'm just hoping as a prerequisite. Okay, so today we'll be building a simple neural network, and we'll be talking about how to implement them with TensorFlow, right? And we'll be talking about some of the features, right, of the neural network. We have a simple neural network, the input layer, the hidden layer, the output layer, right? Uh, um, Like I said, the input layer is most likely where you get input from, and it can represent a number of features that you want to use, like in machine learning. When you have the tabular data, right, there's some features that you want to use to train. So the input layer, just think of it as most of the times, I don't know if you guys can just imagine a circle, right? Circles, right? So your input features are the input features. So right in this picture, you see like two neurons. That means you are representing two input features, right? You can call this whole place the input layer, the hidden layer, and the output layer, right? Or we can say it's mapping to the output layer, anyone. And yeah, so let me go back there. I will share this notebook after the class, actually, so you can look at that visualization. There's the hidden layer. There's the number of neurons in the hidden layer, right? There could be 10, there could be 100 of this, right? This hidden layer here. There could be 10, this is just four neurons, right? And there could be like 100 of them. Uh, there is the output layer representing the number of classes you have, right? It could be binary, where it's just one, and it could be multi-class, where there are more than one, like four classes, right? Imagine you have an image and you want to classify if in that image there are, if it's a dog, a cat, or a person, or food, right? So you can just the number of classes you want to create, you create the number of neurons per class, right? And the technical part of the neural network are the activations, right? Um, the ReLU is an activation function, right? Where it helps the neural network to like it lets it get nonlinear, right? It maps it to different species. Without the activation function, you're most likely just fitting a linear regression model. Like, no matter the number of layers you stack upon it, you're just going to get a straight line. But we'll see it here, right? There's not the output activation, the sigmoid, if it's binary classification. I wish I can pull up images for you. The sigmoid activation function. Uh, hope there'll be images here. So, no, this is the formula for it. And if you guys can see this image here, so what that stands for is like this is like a probability mass function, something like that, right? So if you have an x value over at this side, you get a probability of close to zero. And if you have an absolute over at this side, you have a probability close to one, right? So this is just how it is. Right. So the closer it is to these extremes, the more the probability, like the higher or lower the probability, right? And this is the method, this is the function, right? So whatever the value of z you put into here determines the probability you get out, right? So most likely, if you've done probabilities, you know that probability is most likely for two classes, right? Probability of it being like this, or one minus probability of it being like this. Probability of success will be one. Probability of failure is zero, one minus success, right? So something like that. Then there's now the soft marks for multi-class, right? The soft mark is most likely the normalized version of it, right? So it's you can now have like a whole probability like matrix out of the soft marks. The loss function, there's a cross entropy for binary, and all of these can be checked on their documentation, right? So in this whole data science field, what will help you is the documentation. It's a binary cross entropy. All right, so you can see that from the name, you know that if you're dealing with two classes, not like you have the binary cross entropy as a loss. Um, okay. Okay, so we'll be looking at all of these, and if you want a book or material to assist you to learn, there's this popular book, Hands-on Machine Learning with Second Learn. Yeah, this particular book, and I think it's available online. You can just get a PDF, but I'm not sure of the edition you'll be getting online. I don't know, I'm not sure of the edition you'll be getting. But this book is really helpful if you want to get hands-on with a lot of all this. So okay. Um, so let's go. So I'm going to import TensorFlow and CF. I'm going to run everything again. Just take some time to just restart. After this session, I can look at them. Okay, I think I skipped the optimizer part, right? The optimizer is how um the model, right? It gets to a particular like it reduces the loss, right? Right. This is how the model learns with an optimizer, right? So if you've heard of stochastic gradient descent, you know that it's you have an initial loss function and it's something like this propagation, and as epochs go, you increase the loss function reduces, right? As the time goes. So okay, so today I'll be doing a simple example. I'll be doing just a sample example, right? Something that we can see as we go. So I'm going to create a sample data set. There's a method in sklearn called make circles, right? And you determine the number of samples of a circle, the noise, like so what we're just going to do is I'm going to visualize this, right? So just be patient with me. Right. So um it's just going to let's imagine it's going to give us circles, right? Two circles, right? And if I run this, I can see the matrix of X and I can see the classes you get. I can see the classes one and zero. So this is a binary classification task from what you can see here, right? So what make circle does is create circles. They give you samples of circles, right? And now I'm going to build a model to help us classify each class, right? Is this circle in this class or is this circle in another class? That's where the neural network will come in, right? So I'm going to just create a data frame of it, and I'm going to show you the head. So this is the coordinates of one circle, the x-axis and y-axis. Because if you want to plot something on the graph, you have an x-axis, you have the y-axis, and there's now the label showing which class this particular circle is going to be in, right? So if you do the value count, you see that there are 500 in both classes. And if you plot it, I told you if you're patient with me, I was going to visualize everything for you. And so this is the circle, right? So what we're going to do is we're going to build a model that can distinguish each class of this in this each class in this diagram or in this problem or in here in this image. Right. So the blue represents one class and the red represents another class. Right. So we're going to find a way to build a model. So if you give it a sample example in any place, it can help us classify, okay, if there was one in the middle here, it's most likely going to be blue. If there's one in the extreme here, it's most likely going to be red. So how is the model going to do that? So that's what we're going to build upon. Okay. All right, so let's go. So I'm going to show us the shapes, right? The shape of each, the X and the Y, right? I hope we're following me. You are following with me, right? This is the this is the features. These are the features. The X, right? The features, and Y is your label, right? So here we have it's not like going to be it's going to be two input neurons, right? Because we have two features, X naught and X1, representing the X-axis and the Y-axis. So example, this dot has an X-axis and it has the Y-axis, and we're plotting it, right? We are still with me. So the there are going to be 1,000 samples of that, like we all know. This is a matrix of 1,000 by 2. This is a vector of 1,000. And if you pick out the first examples of each of that, we see that this particular example is of class 1. So that's that about all of that generating the data set we're going to be using. So the next thing we're going to do is go straight to modeling. So like I said, we have imported TensorFlow, working strictly with TensorFlow. There's an opportunity of you to use Keras, right? But I feel if you want to learn, if you want to be, if you want to have control over everything, you have to use TensorFlow, right? So, first thing we're going to do, we're going to create a seed, right? So whatever I do here, if you can replicate it on your end, right? You have the same results. So setting seed is almost um like controlling, making it deterministic, right? Something like that, something of that sort. So the first thing to do is that if you want to create a model in TensorFlow, there are different ways to do it. There's a functional API and a sequential API. The sequential API is easiest to go, right? Where you create a list, right? This is a list, right? And in each list, you now append a- every layer you want. So what we're doing here is we have our input layer. This is going to be our hidden layer, and this is going to be our output layer, something of that sort. Okay. So I just want to type in that. All right. So let me recap that. So in if you want to use the sequential API, the sequential API accepts an iterable list. I don't know if it accepts a tuple, right? So in the sequential API, you create a list, and in every list you append a this dense represents like one layer, right? It gives you the control of one neural network layer, just a regular densely connected neural network layer, like the documentation says. So in this layer, you can control the neurons you want, right? Remember what I said about the neurons? The neurons just represents these circles here. This is a neuron, this is another neuron, this is another neuron, this is another. So that's the whole four neurons. So, but in this simple case, right, we are just going to use one neuron in the hidden layer and one neuron in the output layer. Okay. And now, after you create your sequential API, you've added all the layers you want, then you compile the model, right? That's step two, right? Step two is to compile your model. And to compile your model, you put a loss function, an optimizer, and a metric. Uh, model.compile. Where can I find you? TF. Compile. Then let's see, compile. Well, I can always search here. not sure now. Okay, this documentation is, let me look at that again. Okay, is a method in the sequential API. So let me set the sequential API, sequential instead. Okay, so this is sequential API, right? You have every documentation you need from here. So in this AP, in this method, there are now other methods in it, right? There's a compile. That's what I was looking for. In a compile, you have a specific number of parameters you can pass in. I don't know if you need all of these. The most important one is that the first three is put in. There's the optimizer, the loss, and the metrics. And all of these stand for something. And if you've done like a precursor on neural networks, we know that the loss function is how we generate the loss outside, right? The final loss that it will show you. And like I said, if it's a binary classification task, most likely you want to use binary cosine entropy loss, right? Um, then the optimizer, how does it do back propagation? How does the model learn? How does the model learn in each step? How does it learn? So we are going to use simple stochastic gradient descent. And if you've done any course in deep learning, um, I don't know how many of us have taken this course by Andrew NG, deep learning specialization. It's a good course. I took it when I was starting my journey, and it has a whole lot of like everything you need, and it's going to also teach you about a whole lot of things in neural networks and hyperpointer tuning. So I'm just saying, if you're really interested, you can look at that course too. And also the metrics, right? Like as in machine learning, there's always metric you want to use to evaluate your model. And we're going to use just statistical accuracy. We can also put in mean squared error and mean absolute error, whatnot. Yeah, metrics. So yeah, you can put MSC accuracy. You can put, yeah, there are a whole lot of them, right? So you just need to check that documentation. Most likely in this documentation to see which one you can use. Okay. So let's fit the model, right? So after compiling your model, determining the loss function, the optimizer, the metrics you want to use, then you fit. Right? This is where the actual training is. Right. So you give it your, like we always do in machine learning, you call the fit method. You put in your training set, or for this case, we're just using all the data sets, right? So we're going to give it the X and Y, the label, the feature and label, the number of steps you want it to take. That's epochs, number of steps. And verbose, as the name suggests, it's like, do you want to print out something? Do you want to print out something each step, or you don't want to print out something? So if you set verbose to 0, they're not going to, it's not going to print out anything, right? So let me just train this model. And we'll be take note of the loss and the accuracy. So as it's training, we see the loss is decreasing somehow, right? But the accuracy is just staying about 0.5, right? It's not changing. It's just staying just bouncing around 0.5. And you know what a 0.5 accuracy is? It's almost the same thing as a random guess, right? Like, so this model right now is just doing random guess. It's not better than random guess, right? So as we go on, we'll find a way to improve the model. What do we need to add? What do we need to subtract? No, not subtract. What do we need to add to the model to make it to get better? Right. So it's going to be a step-by-step guide. So stay with me. And so if we do the model evaluate on the same training set, this is not best practice, right? To train and evaluate on the same data set is not best practice, but it's just for teaching purposes here. So we see that the loss is about 0.6 and the accuracy is staying at 0.5, right? So it's just random guess. And now we're going to go to the part where we're going to improve our model, right? Get it to get better than just random guess. Okay, so if you want to improve your model, there are a number of things you can do. The first thing you can do, you can make it change it from a small model to a larger model by adding more layers, right? You can add more dense neural network layers in this case. You can add 10, you can add 100, depending. But be careful of overfitting, right? Neural networks tend to be overfitting monsters, right? They overfit a lot. So you can add more dense layers. You can add more neurons in a dense layer, right? You can see from here, just 4 neurons and it changed to 100 neurons, right? You can now change the activation function. Like in the previous stage, we didn't put activation function, right? We just put it like that. Like I said, what that's going to do is going to just do simple linear regression, right? It's just going to do linear regression. So it's just going to model a straight line. Because what these activation functions do like really rectified linear units, the ReLU activation function. So it's somewhat like a activation. It introduces the probability of non-linearity to a deep learning model and solve the partnership gradient issue. There's no important about that. The most important thing is the non-linearity issue, right? The non-linearity property of ReLU. And we're going to talk about that as we go, right? So we can also change optimization function. The issue with stochastic gradient descent is that stochastic gradient descent is slow, right? In the beginning stages of neural networks before transformers and ChatGPT, we're bothered about how to learn faster. That's when stochastic gradient descent came up. Then I think there's Ada Grad, there's now Adam, and I think Adam is the standard, right? Even maybe transformers use Adam, right? But Adam is standard. It's faster. It prevents vanishing. It prevents. There's something called it's a kind of like slowing down, right? Vanishing gradient in training, right? It prevents that, and also improves the accuracy, right? Because it's faster. We can also change the learning rate. Learning rate as in this. When we're doing stochastic gradient descent, we didn't do anything. We just left it as that, right? But there's a way you can always change the learning rate in. Let me look at the documentation. I hope it pops out, right? So we set the default learning rate, and the default learning rate is zero. Why is it doing like this? Oh, okay. The default learning rate is 0.01, and you can always change that. The learning rate is just like it tells you how fast do you want this model to train, and you want to make it not too big because if it's big, it tends to overshoot, right? It just dances all around the local minima or the global minima. Um, and you can also fit on more data, like in machine learning, in deep learning. Deep learning is a sucker for big data. It's a server for large millions of rows, right? So if you have if you have a data set that is almost like a million rows, right? Most likely want to use deep learning for that, right? That's where deep learning shines over machine learning, right? And it can also fit for longer. And fit for longer is most likely the last case scenario because fitting for longer tends to create something called overfitting, right? Overfitting as in it has learned, you see training accuracy very low, or very high. Like you can have a training accuracy of 0.9. Then when you test, you get the test data, you just have 0.8, 0.7. That's overfitting, right? We all know that now. So that's danger of fitting for longer. And neural networks are very good at overfitting. So you have to be careful of just fitting for longer. So right now, the first thing we're going to do for model 3, we're building iteratively. We're going to add a hidden layer of 100 neurons, hidden layer of 10 neurons, and the ASP layer of 1. We're going to use the binary entropy loss. We're going to switch from stochastic gradient descent to Adam, because like I said, Adam is better, right? It's faster. And we're going to train for 100 epochs, right? And let's see if it's going to update, it's going to make our model better. Let's see, right? Just by adding neurons, it's going to make it better. So also we can also see here once again that it's still dancing around 0.5, still dancing around 0.5, and I don't expect it to be any performing better than a previous one that was still 0.5. So there's something we're not doing right. So before we go on, I'm going to be plotting a lot of things, right? So we can see what's happening in the background. When you get this notebook, I really hope like you go through it, like go through every single method in this place, right? Especially here, right? Go through every single method, and I can just provide like a simple overview. Is what we're going to do, we're going to plot decision boundaries, right? So to plot decision boundaries, we need to get a like if you did physics, right? If you did physics, you know that to plot something, you need a set of values. And so you need like a matrix. So we want to plot in those matrix, those values there. We're going to predict, and we're going to give it, if it's a multi-class, is different. If it's binary class, we're going to round it up. Then we're going to plot a decision boundary with the contour F um, function. This is just creating a metric grid. Metric is just like a matrix, right, of values you want to plot, right? So just go through it, and if you don't understand it, there's always Stack Overflow for you to understand what is the metric grid and any questions you have. So we're going to plot the decision boundary of this model we just built here and see what is actually going on. And if you look at it, you can see that, like I was always saying, because we didn't add the non-linearity, it's just going to do linear regression for us, right? Simple, just going to plot a simple line. And we can see that on the left-hand side and right-hand side, they're almost the same. So that's why it's having a 0.5 accuracy. It's just random guess, right? It's just guessing. That's what it's doing. So right now we're going to try to add a activation function that's going to give us the non-linearity. And we're going to see the difference between not with the one with non-linearity and one without non-linearity. All right, so what did we change here? We just use 4 neurons, the two hidden layers, hidden layer 1, hidden layer 2, with an activation function, right? I was specifying a Rayleigh activation function. Rayleigh activation function, that's the most popular. I don't know if you want to you need another one, right? Rayleigh is the most popular. And like I said, in the field of machine learning and deep learning, there's been a lot of research. There's the GELU, there's there are a lot of there's the LU, there's a prelude, and a whole lot of different things, right, that they came up with in their research. And most of the times, the trade-off with all of these other activation function is not even as great as just using your standard value. So most of the times, even in something like ChatGPT, they just use the rectified linear units, right? And it's not always all about complexity. So the ReLU, then this is the aspect layer, just one because we're working with binary classification, like I said. This is model 6. This is our sixth iteration. We're using binary cross entropy. We're using the same Adam. We're specifying a learning rate of 0.001, which is actually the default value. So there's no even need of specifying it, right? The default value is already 0.001. So there's no need to specify it, but I'm just specifying it, right? Just for visual purposes. And we're leaving the metric as accuracy. Right now, we're going to fit and see what's going to happen in this case. Since we added the Rayleigh activation function, what's going to happen? So we are seeing the accuracy. All right, it was decreasing at some point, and I was scared, like what's happening here. And now we are seeing it increasing, and it's steadying at 0.9. Where are you going to steady at? Okay, we're seeing 0.988. But let's be sure. Oh, okay. 0.988. Wow, I don't know what just happened. And I think I know, but so what's going to happen is that the thing about training with a GPU is that training with a GPU is most likely going to be saving your models in space, right? And you're going to end up having something like this. So what I'm going to do is I'm going to restart the kernel. I'm going to delete the runtime and start it again because it's most likely saved everything I've done. All right, so let me restart it and run everything from beginning again. I can see there are no questions for now. Okay, looks like everyone is running with me. So I'm going to run everything from before this and hope it doesn't do this again. Shouldn't though.
Well done, Emeka. There's question. No.
Okay, after the session, wow, one said, um, sorry about that. Okay, I think I can take the question while this is loading.
Okay. Thank you very much for this introductory class on neural networks. I have a lot of reading and catching up to do on neural networks, and I thank you also for recommending the book on Anton in machine learning. I already gotten it, and I know that that would be very helpful. So, you somewhere in between when you're mentioning using TensorFlow, that you mentioned that it can give us more control. Then you said that as compared to using Keras. But I know Keras, at least based on what I've read so far, is built on TensorFlow.
So
So
flow, yeah.
I wanted to understand, like, what does that mean? So I will not be losing what it means or what you're trying to say.
Okay, what does it mean? What's Keras? What's TensorFlow? Like, is
Yes,
that
as
what you want
per
to know? What you
what
want to
does it
know?
mean to use to not use Keras but use TensorFlow so you can have more control? What like
All right. Okay, the thing about Keras is the higher level API, right? And when they say higher level API, is that Keras is going to simplify a lot of things, just like how will I put it now? Let me give you an example. Scikit-learn, right? Just imagine the days before Scikit-learn. What were they doing to plot to build their models, right? They were most likely using NumPy, and they were doing everything all by themselves, doing all the gradient descent, all the training with just simple Python and NumPy. That's very, very low level, right? That's very, very low level. And they could control what was happening in between in everything. But what scikit-learn now brought is that you just need to get your data, call the dot fit method, right? And under the hood, scikit-learn is implementing everything that you would have implemented before, right? So same thing with Keras. Keras will just you just need to call a simple function instead of doing all of this. You most likely need to just call a simple um let me say a simple method or so that will help you like do all of this and you just need to call dot fit, right? Instead of building all of this with the sequential API and or whatnot. Right? Do you understand what I'm saying? Do you understand what I'm saying?
Yeah, yeah, thank you so
Right
much. It actually
now,
makes a lot of
right
sense.
now, okay, okay. Even right now, I think we're using Keras, like because of this dot Keras here. But
Yeah, I
on,
saw
we're
Docker
not using,
singularly.
yeah, we're using Keras, but we're not using all of Keras because of the activation functions we're using. it's not all of Keras, right? You can implement Keras and TensorFlow, but if you want to control like how the training is going, right, you most likely just use TensorFlow. That's yeah, I hope I explain it well for you.
Yes, it made so much sense. Thank you.
Right.
I really could relate to the example when you say how would they build their models before scikit-learn was developed. They had to use NumPy and Python, so low level, but they could control every single piece and part of the model, as compared to just everything being automated because we have already bigger libraries that have bigger functions. Okay, thank you very much.
Yeah. Yeah. Wow. Okay. Now let's plot it. Sorry about that. Yeah. So we can see that it's not that great, but it's still better than 0.5, actually. It's still better than 0.5, but there's still something we need to do, right? But if you can zoom in closely, you can see these zag lines, right? This is what the ReLU has done for us. Like it helps us like not just plot a straight line, right? It puts that nonlinearity. And nonlinearity means something that is non-linear. Don't mind the whole nonlinearity term you're getting, I might be. So this is just linear, and nonlinearity just means something that is not just a straight line, something that has a bend or a curve or something like that, right? So the last thing we need to add now is the sigmoid output. The sigmoid output as in um you want to output probabilities, right? Instead of just outputting scores. Right now, let me just recap. I hope I don't lose any. Yeah. Right now, what we're outputting are a set of numbers, right? Set of numbers, just like almost regression, right? So that's why we're getting something like this, right? Just numbers. It's just so, but with probabilities now, with probabilities, the binary cross entropy function kicks in. And if you've taken, well, don't worry, there's a formula for binary cross entropy, the cross entropy function. So what it does is that if you give it a probability, it's going to give you an output, a score. Why am I getting this? I'll come to Nigeria. Okay, hope this how you can. Yeah. Wow, I'm not a robot. Wow, brilliant now. Okay, so this is the this is the formula. Don't get lost with it. So what it just does is that it collects probabilities, and from those probabilities, it's going to output it's going to give an output, right? So that probability will now tell us that is it good? Those probabilities now, okay, let me track back. Imagine you have an image of a pig. You have is this a cat or not a cat? You want to train a model, is this a cat or not a cat? So a high probability means it's a cat. A low probability means it's not a cat. So what the cross entropy loss function is going to do is that if you compute a high probability when it is not a cat, it's going to give you a very, very high loss because you are wrong here, right? Because you are wrong here, it's going to give you a very, very high loss. But if you compute a high probability like 0.9 and the picture is actually a cat, that means you are very close. Yeah, you want it to be a 1, but it's a 0.9, which is very close. So it's going to give you a very low loss, right? So it's not going to penalize you because you're not far off. So that's what all of this function is doing here, right? That's what it's just doing. Mathematicians just came up with a function to make it a value. Right? So now we're going to add a sigmoid, and we're going to leave everything as it was, right? And we're not going to train. I put the variables at 0, so it's not going to show us an output, but we're going to wait for it to be done. And we're going to evaluate and see how good it is. I'm most likely giving a spoiler. But yeah, um, if we evaluate and we plot the decision boundary, what am I running? We see that now the decision boundaries are much better, right? They are much better. They are much in tune with what is actually there. And we see that we have a 99% and a 9.5% accuracy, which is better than the 0.5. Okay. So in a normal sense, you won't want to train your model on you're not going to evaluate your model on the same data you used to train it because you're not going to evaluate it properly. You need to have a training set, a validation set, and a test set. But you can always make the validation optional, right? For our case here, this is just simple use case. So what we're going to do, we're going to create a split, right? A train test split, and we're just going to separate it by 800, 80% and 20%, right? And now we're going to train that same model on the train set and on the train features and target train features. And we're going to evaluate on the test set to see how well it did. And we're going to know whether it's overfitting or not. This is model 8. Let's change anything. Change it. Let's see. I'm not supposed to get this. I'm running all of this. Model 7. Model 8 sequential. All right. Let me just leave it. Okay, for faster training. But let me turn this to 50. Right, so we can get a better score because I don't like what I was getting here. It's still bouncing around that. It's quite weird. Let me call model 7 on this instead. It's most likely because of these strings. I don't know if there's been some changes with their API, and some of these changes always affect your output because this is the same thing as model 7, but it's still not training as good as model 7. So let me use model 7 on, no, let me use model 7 and evaluate instead and see how good it was. Maybe it's going to be 100%. The dangers of running so many models in one place, right? The thing about all of this is that on your GPU, it's storing a lot of matrices and calling a lot of models. It's better for you to restart your kernel and clear all of those memory in your GPU and start it fresh. But yeah, this is just how it is. Most of all these things are bugs in Jupyter Notebook. Sorry, Colab, right? So bear with me. So what I'll do is that I'll most likely call it on model 7 instead, right? Even though that's not right. On your own end, I'll prefer you guys to call it on model 8, right? Instead of running all of that, just run model 8 and see what it gives you. Like I said, the issue is that because of all of everything in GPU, it's going to throw us some errors. But wait, let me just use this instead. Let me see this to calculate. See, it's better this time because it's not supposed to throw me this issue. still bouncing around that. So I don't want to restart this kernel again because it's going to take some time, and I've already taken 48 minutes for this simple intro. So what I'll do is just draw the decision boundaries of the model 7 and show you how it is. Okay, so like I said, it's always better to have a train set and test set and plot most of all these decision boundaries and evaluate on a test set, train on a train set and stuff like that because you get a clearer sense of whether your model is overfitting or not, right? So when you get this model, I'll advise you when you get to model 8, um, try to clear the runtime and run just this all over again and see what it gives you. And hopefully it doesn't give you this error I'm getting. So the last thing is to plot the loss and training loss and accuracy, right? So most of the times when you are doing your training, you want to see how it's getting better. Like you want to always plot most of all these things because you get a sense of whether your model is overfitting or not with your training curve. In machine learning, in deep learning especially, if if you can see the curve, you can know whether your model is getting better or is getting worse. Because most of the time, it's going to be a long training process, and you want to see when to stop it or not, or whether it's getting better than just waiting and seeing that it's all gone wrong, right? So that's where the curves come in most of the times. And this is just model 8 on. There's still a lot of going down to do, right? So when you get this model, train on a larger epoch for this model 8 and also see if it gets better. Right. So that'll be the end of today's class. Right. And in the notebook, you have something like a playground where you can play around with this visualization. There's this visualization that Google made when we all started getting hype of neural networks, where you can play around with these figures and you see like what it all means, right? So come here, play with it and see how the output is. And I think you get a better sense of what's happening with the neural network on your neural network. So yeah, that's the end of the class for today. If you have any questions, you can drop them in the chat. Okay. Olusegun, if you can ask a question.
Okay, good afternoon. Thanks so much for
Yeah,
your
good afternoon.
for the effort you're taking to explain this to us. Okay, so I've been building a lot of models, but I'm not so conversant with deep learning. So um, in fact, when I was going through the notebook, I mean the course for this stage D, I was not too clear about so many things. The data set that was given to us, that digit MNIST, digit recognizer was imported and the rest. So I was thinking that for the coding section, we're going to use that same data set and explain the all those code snippets so that it will be more clearer. I don't know how go up on
There's still
this
another
regard.
session. There's still another session. So
Okay.
we can in
All
next
right.
session
Okay. Thank
maybe
you.
I'll go through that will be on Thursday.
Okay. Okay. Thank you very much.
All
That
right.
would be much appreciated.
All right. All right. All right. If there are no other questions, have a nice day. Um, always try out that you can always download that PDF and walk through with it. So if you get lost, always ask questions from your peers. So yeah, deep learning is a very, very intense field, and yeah, you most likely have to do a lot of YouTubing to get better understanding. All right. I'll also share the notebook with Amoye.